I'm Julien Morin from University of Montpellier, and I will present here a selection of first results from Spheru, focusing on cool dwarfs, so K and M dwarfs. And this is obviously the work of a lot of people in the Spheru legacy survey team. So what I will do in this talk first is to remind you what the Spheru instrument is, what we want to do with Spheru within the Spheru legacy survey, and I will show you a couple of results for two K dwarfs and a few other results for M dwarfs. So first, Spheru. So Spheru, as you certainly know, is a high-resolution near-infrared spectropolarimeter, which covers basically from a Y to K band, and even actually the actual performance is a bit beyond K band. It goes almost to 2.5 micron at high spectral resolution, around 70,000. And the idea is that we can reach high SNR for M dwarfs with J magnitudes up to 12. The other aspect of Spheru, which makes it specific with respect to previous instruments like Espadon and Narval, is that Spheru is also designed to produce high precision velocimetry in order to be able to detect planets orbiting especially low mass M dwarfs, but also to make velocimetric measurements for young stars as well. On the spectropolarimetry part, so Spheru, as Espadon Narval, is able to deliver both circular and linear polarimetry, and the idea is that it was designed to limit the crosstalk between these two components of the polarization to less than 2%. I will go rapidly through these details, but basically Spheru is built with a case-grain unit, which is directly mounted on the telescope where there is the polarimeter and the ADC. Then it feeds a spectrograph, which is cooled down in a vacuum tank and allows to reach very high stability. And as we are operating in the near-infrared up to almost 2.5 micron, it has to be cooled down to 75K. And obviously, the thermal regulation has to be very efficient if we want to reach very high radial velocity accuracies. Also, so the spectrograph is fiber-fed, and this is, again, optimized for both transmission and stability. So Spheru arrived at CFHT in early 2018. It was actually commissioned at the end of that year, and there have been some improvements ongoing on the instrument since then. For instance, at the end of 2018, laser frequency comb was installed, which is expected to allow us to reach even higher radial velocity accuracies. There were first some tests in Toulouse, and then more tests performed on the sky at CFHT. Many spectra were collected for that, and actually part of the results I will show afterwards are either from science verification or commissioning in the Spheru dataset. So now that I have reminded what Spheru is, so what do we want to do with it? So Spheru is mounted basically at CFHT as an instrument open to the community, to the CFHT community, which can be used for a variety of programs which require high-resolution spectroscopy, spectropolarimetry, and or radial velocity, high accuracy radial velocity measurements in the infrared. But in addition to being available to the community, it is also used extensively for a large program called the Spheru Legacy Survey. There are two main goals in this survey. The first one is to detect planetary systems around nearby M dwarfs, so to detect and characterize them. In order to do that, we want to be able to model and filter the activity, and that's also a reason why we go to the infrared and why we have polarimetry, and the idea is to be a sort of follow-up of what was already started on the harps of Sophie, but which were less optimized to address the specific topic of M-dwarfs. And obviously, there is a clear synergy with a number of future or present instruments, and especially space missions such as TESS, as I will show later on. The other main aspect of the Spheru Legacy Survey is to study the impact, the role of magnetic field in star-planet formations by studying the magnetic topologies of young stars and also for some very young emitted objects of the disks themselves, and to try to detect young close-in planets, so like hot Jupiters from very early in the story of the star, where they are still at the tertiary phase, as was already done by the pioneering works conducted with Espadon at the end of the, well, just before SPIRou was operational. And again, there are some synergies with a number of instruments such as ALMA, SPHERU, and also JWST. In addition to these two main goals, so planetary system of nearby M-dwarfs and the role of magnetic field in star-planet formation, there are also some complementary goals. For instance, with the capabilities of SPIRou and even with the data collected within the Spheru Legacy Survey for the two main goals, it is possible to study the atmospheres of both M-dwarfs and giant planets. It is also possible, and that's what is mainly interesting us in the BCool community, to study the dynamo processes in fully convective stars with respect to what happens in partly convective stars, because M-dwarfs encompass this transition between partly and fully convective internal structures. And also, we can analyze what is the long-term evolution of the Earth's atmosphere, because basically we are recording a lot of spectra of the Earth's atmosphere in the near infrared. So this is basically what we want to do with SPIRou. And although, as you could see, for the main sequence, our main goal with SPIRou is to study M-dwarfs, and especially to understand how, well, what are the planets orbiting them and how this interact with their magnetic field. We have started with K-dwarfs because it's also a possible application of SPIRou, and it was a good opportunity to see how the results we can obtain with SPIRou in the infrared are related to what you already know at optical wavelength. So first thing is HD 189733. So it is a very well-known K2 dwarf showing some activity, and with a hot Jupiter orbiting it. And it has been extensively studied, especially to try to understand how the magnetic interaction between the star and the planet could occur. Here I show, for instance, a figure extracted from the paper by Wim Fares et al. 2017, showing the evolution of the large-scale magnetic field of this star in the period 2013-2015. So it was already pretty well studied in the optical before SPIRou. Now, what did we get with SPIRou? So we had 48 parametric sequences, plus a series of 86 unpolarized spectra, which were taken both during the commissioning and the beginning of the Spheru Legacy Survey, because Spheru Legacy Survey started in January 2019. So as you can see here, we are on both periods. All the spectra have a very good synergy ratio, and the median one per velocity beam is around 230. What I'm showing here, so all the results on HG 19733 are from this paper by Claire Moutou 2020, and they were all obtained using an older version of the reduction pipeline of SPIRou, the DRS called Apero version 0.5. So it is representative of what were the performances of the SPIRou analysis, SPIRou pipeline, let's say, at the end of 2019, during 2020, but there have been a lot of changes since then, so you should not consider that this is a representative of the present-day performance of SPIRou. Here, what you can see, so on this plot is a raw SPIRou spectrum showing, so in particular, the Blaze function, you can see all the spectral orders, about 50 spectral orders in the SPIRou spectrum. And what is already obvious is that you have all the teric bands. So here showing as deep absorption, corresponding mainly to the water bands in the Earth atmosphere. So obviously in the infrared, that's something which is changing a lot with respect to the optical. Here is an example again of a small chunk of a Spheru spectrum in the H band around 1.6 micron, showing in black the raw spectrum, in green the teric model with both absorption line and OH emission lines, and in red you have the teric corrected spectrum, showing that already at that point the DRS were doing a pretty good job to correct for teric absorption, which has again improved since then. So what do we get with Spheru? Basically, from this data set, we reach photon noise contribution in the final radial velocity budget of around 1.5 meters per second. Within a parametric sequence, we see a dispersion, an average dispersion of about 6 meters per second. And if we model the orbit of the planet, we see that the out-of-transit residual are around 10 meters per second. This can be compared with what was obtained before in the optical. In the optical, it was observed that the scatter was between 9 and 15 meters per second. So we are rather on the lower part of the scatter, which is what we expected, because we expect to have slightly decreased radial velocity jitter in the infrared. So this is what we expected. And also, if we compare what is the radial velocity content in the difference wavelength domain of Spheru, we see that most of the RV information is in the H band. You can see so here what is the residual, and you can see especially that there is a very clear rotational modulation for all the points which are marked with a red square, which were acquired during a given rotation cycle. And you see that most of the residual we see has to be actually related to stellar activity, is coherent with is varying coherently with the rotation of the star. Also, the Rossiter effect was observed. The residual of the fit to the Rossiter effect is around 5 meters per second, and we obtained a fit which is compatible with previous works carried out mostly in the optical. So all this looks very good. Also, we could make a first analysis of the magnetic field of the star. So we used an LSD mask composed of around 4,000 atomic lines. The polarimetric precision which is reached is a few times 10 to the -5 the level of the unpolarized continuum, which is what was expected and similar to what we could reach with a Spad-Bond Narval. And we can measure longitudinal magnetic fields of a few Gauss, which are of the same order of magnitude of what was observed in the optical, although no direct strong comparison is possible because there was no contemporaneous optical observations. And we can see again that there is a clear rotational modulation of the longitudinal magnetic field during the rotation of the star. Also, it was possible to measure magnetic field from Stokes-side profiles, so you're measuring directly the Zeeman broadening. So this part of the work was performed by Colin Folsom by selecting 4 iron 1 lines located around 1.5, 1.6 micron. 3 of them with high Landé factors and 1 of them with almost 0 Landé factor, in order to be able to model the average magnetic field, which was found to be around 300 Gauss. On the other hand, it's not possible to detect any specific broadening if we compare LSD profiles computing from separating high and low Landé factor lines. Also, there is a slight hint of a possible correlation between BL and BF values, which would also be a hint that we can sort of see modulation in the BF value, but this is to be further investigated. So this was for our first K-dwarf, so HD 189733. Now we can also address another well-known active K-dwarf target that many people in the BCool community know very well. It is Epsilon Eridani. Again, a K2 dwarf with 1 planet clay, maybe more. And here you can see, again, examples of magnetic maps reconstructed from 2013 and 14 data sets in the paper by Sandra Jeffers, 2017. So again, a star that we know very well in the optical. In this case, 4 Spheru spectra were obtained during the science verification, to which were added 20 novel parametric sequences obtained contemporaneously, and also test photometry, 30-day test photometry obtained at the same time in September, November 2018. Here we reach a very high signal-to-noise ratio, around 1000, because the star is very bright, magnitude about 2. And you can see here, for instance, an example of the Echelle Narval spectrum, showing a very nice spectra with a lot of stellar spectral lines and a few telluric bands, mostly in the red part. If now you go to the Spheru spectrum, you can see that it's quite another story, because most of the spectral lines you see actually in the spectrum this time are telluric lines coming from the Earth atmosphere. And again, the Spheru map line already did at that time a great job at removing the telluric contribution and showing only the stellar spectral lines. In this case, Colin Folsom performed in this paper, so all the results again I'm showing are from the paper by Pascal Petit et al. 2021, and in this case, so Colin Folsom performed a fit of the spectra both in the optical and the infrared, and showed that we could get compatible stellar parameters, except for the macroturbulent velocity, which is still to be further investigated, why there is this apparent discrepancy in the turbulent velocities between the optical and the infrared. For the large-scale magnetic field, we measure magnetic fields of a few gauss. This time, as we have the contemporaneous observation, we see clearly that there is a good agreement between the two instruments, although the Spheru error bar is a bit larger than the Narval one, because basically the instrument, well, let's say that there are less lines and deep lines in the Spheru domain, and we don't have the same gain in signal-to-noise ratio as we have for the M dwarfs.
10 minutes, Julien.
Also, okay, thanks. The average field was studied using Stokes eye, and again, it is possible to measure magnetic fields of around 250-300 Gauss. Now, a few results for M dwarfs. So there are two subtopics I want to show now. One is a Eumic, again, a well-known M dwarf young star of about 22 million years with an edge-on debris disk. And for a Eumic, transiting hot Neptune planet was discovered a bit before the Spheru runs from test photometry. So this is the discovery light curve for a Eumic B, so a hot Neptune orbiting at about 8.5 days. And for Spheru data, we obtained 27 parametric sequences with, again, high signal-to-noise ratio. The estimated RV accuracy is of the order of 5 meters per second there, including 2 to 3 meters per second of photon noise. But the radial velocity dispersion is much higher, of about 45 meters per second, which was expected because a Eumic is a very active star, and probably and certainly not representative of what are most of the stars in the Spheru legacy survey. From this Spheru time series, it's possible to clearly detect the planet at 3.5 sigma, if we take into account the activity as it's done here. Also, we clearly detect circular polarization in spectral lines, which allows us to model the large-scale magnetic topology of the field, and also to see that this modulation of the Stokes eye profiles represented here by this brightness distribution allow us also to clearly filter out the activity in radial velocity measurements and detect the planet. Also, it's interesting to see that there is here what you can see a clear variability of the width of the high Landé factor lines, which is clearly correlated with the radial velocity of the star, which shows that there is also a good, it's also a good way to track activity jitter in M dwarfs in the near infrared. And also, again, the Rossiter-McLaughlin effect was modeled with a residual of about 5 meters per second, and showing also here on this data set the intrinsic instrument stability of about 0.5 meter per second. Finally, for the M dwarfs also, we can say a few words about what I call the usual suspects. So the stars which are in this diagram, my favorite and not confusing at all diagrams, a diagram showing the M dwarfs in the mass period plane and showing the magnetic properties. A number of these stars are observed within the Spheru legacy survey because we have included a few active stars provided they had low VSI9. What I can show already concerning stellar activity is that we see some evolution of the large-scale magnetic field. For instance, here on the top plot, in this plots produced by Stefano Bellotti, we see that for AD LEO, the BL is evolving. So there was already a hint of evolution as observed by Alexis Lavai in 2016. And now we see from data acquired in 2019 and 20 that definitely both the large scale and small scale magnetic field of AD LEO are evolving with time on a time scale of 10 years. Also, on the bottom panel, you see similar kind of things for EVLAC. We clearly see that there is an evolution of the field. In this time, it's not the average magnetic field which changes, but the amplitude of the modulation of the field. And to understand that a bit more, we'll need to resort to ZDI modeling of the star. Also, we clearly see that there is Zeeman broadening in the LSD profiles, on the average profile, in this case, for these very active stars. And if we split the line list between high and low activity stars, we can clearly see that there is a clear broadening on the average lines. Ongoing work includes joint naval and SPIRou observation to better understand how the large-scale field evolves and how it compares, how what we can infer compares in the optical and the infrared. And also we are working on optimization of the infrared line list for radial velocity measurements and correction of the activity jitter. So as a short summary, SPIRou provides accurate parametric and radial velocity measurements in the infrared. The SLA started since 2019A. We have already a handful of interesting results on K-dwarfs, M-dwarfs, and also on transiting planet or T-Tauri stars, which I did not show. Radial velocity accuracy is always increasing because it's the pipeline is continuously being improved. And also we have a clear perspective for getting interesting results, not only from the polarimetric information, but also for the Zeeman broadening. And there is a lot of work going on Spheru, especially for M-dwarfs. And also SPIP, a copy of Spheru at TBL should arrive next year. So stay tuned, more is coming on the Spheru side. Thank you for your attention.
Thank you, Julien. We're running a little bit behind, but maybe we have time for just one quick question, if there are any. Stunned into silence. No, we've got one from Alexi.
Seem to be no other questions. Maybe I can ask mine, Sami, here.
Well, Alexi had his hand up, I think. No.
Oh, sorry, I missed that. Okay, then
go first, Sami, it's fine, it's fine.
Sorry about that. Do you, if I understood correctly, with Spheru, you can also measure the titanium 1 lines at 2.2 microns, is that correct?
Yes, they are clearly in the Spheru domain, yeah.
Right, because they could be very interesting for the cooler stars. But
yes, definitely. Yeah, for the K-dwarf, Colin used a couple of iron lines, but definitely for M-dwarfs, there are also a number of titanium and sodium lines in the K-band, which are really great, and where we clearly see the splitting. Actually, didn't show it, but we clearly see the splitting.
Yeah, they're very nice. Yeah, thanks. Alexis, all yours.
Do we have time? Otherwise, I can just ask Julien later. It's fine.
It's really quick.
Really quick. Okay. So thanks for the talk. It's beautiful data, and you showed my favorite lines. My quick question was, how do you do the telluric modeling and removal in the pipeline? And is that data product offered to users like telluric removed spectra?
Yes, actually, what I have shown, so from Claire's 2020 paper, this is really what you get from the pipeline. You get the extratic spectrum without telluric correction, the one with telluric correction, as well as the telluric model. And this is done through PCA modeling based on the observation of a number of telluric standards. And it also uses observation of all observation of a given night performed by Spheru to perform this telluric reconstruction.
Nice.